Hello, students. And I hope I gave you some things to think about yesterday in terms of atomic models. And before we get started with today's notes, let's do a quick review from yesterday. Does anyone remember who was responsible for introducing the whole concept of atomos? Democritus is right, the ancient Greek philosopher. Democritus came up with that word atomos, which means indivisible. And in English, we call it atom. And then our first scientist, true scientist in the early 1800s, to add information to that centuries-old idea of atomos from Democritus was a scientist we celebrate this week as our scientist of the week, and his name is John Dalton. And Dalton came up with the ATOM, which stands for the atomic theory of matter, which is made up of 4 points that all elements are made up of indivisible atoms, that atoms of an element are alike, different elements are made of different atoms, and fourth and finally, that it is the atoms that join to form compounds. Which brings us to the third atomic model, which we discussed yesterday, and we ended with our buddy J.J. Thomson. And what was the name of J.J. Thomson's model? The plum pudding model. And so it was J.J. Thomson who was the first to imply that atoms, the consistency of an atom was not the same throughout, because he envisioned in his model that there was positively charged pudding, suspended in which were negatively charged corpuscles. And it's from that model we are going to expand our discussion today with our next scientist called Ernest Rutherford. Ernest Rutherford was another English scientist, and yes, for quite some time in history, Britain was home to the world's greatest scientists, no doubt. But in 1908, this English physicist performed a very famous experiment called the gold foil experiment. And in this gold foil experiment, which I'll explain to you in a moment, he concluded 3 different things. He concluded that an atom had different parts to it. And at its core, at its central nucleus, was a denser part, a part that was more compact than parts around it. And so he suggested that atoms had a dense central nucleus. But more than that, through his observations with his experiment, he also suggested that it was the nucleus, this dense center portion, had a positive electrical charge to it, and that the negatively charged particles, which we would call electrons, were scattered outside the nucleus. So, excuse me. Thank you. Now, that probably made a ruckus, my loud sneeze. And did you know that the average sneeze comes out of a human's nose at about 100 miles per hour? Did you know that? A little bit of sneeze trivia here for today. But I mention it because Ernest Rutherford was able to construct a device that propelled objects at nearly the speed of light. Yes, that's much faster than a sneeze. Absolutely. But here's the deal. His conclusion led him to believe that that an atom was in fact made of different parts, that there was a positively charged central nucleus and negatively charged particles around the nucleus. And while I'm pointing these things out, make sure that you've got this diagram of the atomic model of Ernest Rutherford copied down into your notes. Because this is an important distinction between what J.J. Thomson thought and what future scientists would think. As we go through our continuing story of the history of the atomic model, we will continue to see how it progresses from one model to the next. And take notice here, if you haven't already, how Rutherford's model differs from J.J. Thomson's model. Again, J.J. Thomson was still kind of adhering to this idea that an atom was indivisible. But there were different parts throughout. He couldn't let go of that indivisible idea. Well, Rutherford is a little bit more bold. And he is not only suggesting that an atom is made out of different distinguishable parts, but he also suggested that he was able to separate the different components of an atom. That an atom was inherently no longer indivisible, but capable of being broken down into its smaller components. Let me explain what I mean by that. So here's a diagram of his experiment. And yes, this would be good to have in your notes as well. So let's discuss this. He developed what he called a particle emitter, which essentially shot atoms out at a very fast velocity. It was kind of like the world's first ray gun apparatus. He was shooting out rays. A cathode ray tube is what he was in the forefronts of creating here, the precursor to the television screen, you might say. Not the modern flat screen TV, but the old tube TV. But he had this particle emitter, which he knew shot out atoms. In front of the particle emitter, he hammered down a piece of gold foil. Now, you need to know something about gold. He knew it at his time, and we know it today as well, that gold is extremely malleable. The word malleable means that it can be hammered down to a very, very thin layer. In fact, we know that a little piece of gold can be hammered down so thin it's essentially transparent. You can see through it. In fact, some really expensive cars have a thin layer of gold foil on their windshields. Astronauts that went to the moon had a thin layer of transparent gold on their visors in order to keep out dangerous cosmic rays to avoid going blind. Well, even in the days of the 1800s, Rutherford was aware of these interesting properties of gold. And so he hammered gold down into a very thin layer, which he believed to be one atom thick. An atom of gold thick. That's why it would be transparent. He could see through it. But he put up this gold foil, and behind the gold foil, he had a special type of a screen, and around the gold foil, he had a special type of screen. And they were really doing a lot of experimentation in his day with electricity and the different charges of electricity and the charges of particles and so forth. And he discovered something very interesting. You see, he shot these atoms at the gold foil over and over again, and he noticed that the screen behind the foil would get pummeled in a central location. And through experimentation, he was able to pinpoint that these particles, most of them were positively charged. And he also noticed in the screens around the gold foil, he noticed that there were a few particles that would inherently be bouncing off the gold foil in order to make images on this screen around the front of the gold foil. And he, through experimentation, was able to deduce that these particles were negatively charged. Now, through his experimentation, he was supporting the idea of J.J. Thomson, the idea that atoms were made of positive and negatively charged particles, but he built upon that idea. And the way in which he built upon it is that he believed that the positively charged particles were contained in a more densely located nucleus to the atom, and that's why they were able to go right through the gold foil. And there was a more fluffy material around the nucleus with negatively charged particles that allowed these negative particles to bounce off of the gold foil. So look at his model again. He suggested atoms had a dense central nucleus and that there were negatively charged particles around the nucleus, and that the nucleus was primarily positively charged. It was his famous gold foil experiment which led him to these conclusions. But this isn't the end of the story. In fact, even by the end of our notes, we're not going to get to the end of the story. But let me say that with each new year that is added to our story, new technologies are developed. New biases are taken on by scientists. In addition to the new technology, new concepts, new ideas are presented to the scientific community. And as a result of those big ideas, atomic scientists generally would take these ideas and expand on their atomic models as well. And with that background, let me give you atomic model number 5, proposed by Niels Bohr. Now, it is said that Niels Bohr was the real life of the party. No, I'm not implying that he was boring, that hint of sarcasm there. He actually was a very interesting individual. In fact, he was a contemporary of Albert Einstein. In fact, Niels Bohr and Albert Einstein knew one another quite well and interacted with one another. But in 1913, he was a Danish physicist, by the way. He developed a new idea for the atomic model. You see, back in Niels Bohr's day, in the early part of the 20th century, there was a war going on. And I'm not talking about World War I, which, by the way, it was going on as well. But there was another war, a scientific war between nations to build the biggest telescope, because nations wanted to explore the universe. And in order to do that, they needed bigger and more powerful telescopes. And around this time, people were learning a great deal about the solar system. And many scientists were so excited about the new discoveries of the solar system. We were learning more about the orbits of planets around the sun and the various moons of different planets orbiting the different planets. There was a lot of new discoveries taking place back in the early 20th century as in terms of space science. And it was a really exciting field. And so many scientists had this bias about seeing order in the universe. People could explain with mathematical equations how the planets and the moons and comets and asteroids orbited larger bodies like the sun. And so there was this attempt to explain everything with a mathematical explanation or bias to it. And so this affected Niels Bohr. And as he was studying atoms, he suggested that, golly, we see the order in the universe with the planets orbiting the sun. Perhaps it is the same way on a very small scale, too. And so Niels Bohr suggested that the electrons were like little mini planets orbiting the nucleus, which was like a tiny little sun. And so, according to the electron orbital model of Niels Bohr, which is still somewhat useful today, the electrons move in definite orbits around the nucleus in what he called various energy levels. Now, to put that in picture form, here's what his atomic model looked like. Here we have the dense nucleus, which would be kind of like the sun in a solar system, with electrons orbiting around the nucleus, kind of like planets orbiting around the sun, or like solar systems orbiting around the nucleus or the center of a galaxy. Niels Bohr observed things in nature on a grand scale and thought that it was logical that they might be able to be applied to a smaller scale as well. And I'm not saying that that's wrong. That's just a logical conclusion to make based on your particular biases in the world of science at that time. Now, as I said, the Bohr model here, which is not all that boring, but rather exciting, but this electron orbital model is even today useful for us to understand certain things about how different elements react with one another. In fact, this whole diagram here with the different energy levels, the first, second, and third shells, energy shells, as they are often referred to. This is going to look familiar to us in the next unit of study when we get to chemistry, because we're going to rely on some of Niels Bohr's model to help us understand some of the basic concepts. But for today, we can't stop here because we've learned more about atoms than Niels Bohr was aware of. And so we're going to move on to atomic model number 6, which is called the wave model. It has other names to it as well. It's currently known as the quantum model. But the wave model or quantum model of today, you can't attribute just one scientist to coming up with this model. It is the cumulative effect of many scientists over many years working together on this idea. And the big main point of the wave model is that the electrons are found in an electron cloud around the nucleus. Now, I want to try to explain this with an analogy. Imagine you have a bicycle wheel. How many of you have bicycles? If you don't have a bicycle of your own, I'm sure you've seen a bicycle. Now, imagine taking a bicycle and flipping it upside down so that you could change the tire. Now, imagine you're looking at the back tire. And if you notice the wheel is round. Ooh, let me use a different color here. Here, we've got a round circular wheel. Now, this wheel has spokes that hold it together to a hub. Now, imagine those spokes for a moment, and the wheel is stationary. You can see those individual spokes, right? Hopefully you can picture that. Now imagine you start cranking the pedal faster and faster and faster. When that wheel starts spinning around really super fast, are you even able to see the individual spokes any longer? I don't think so. In fact, you couldn't even tell me exactly where one of the spokes was at a given point in time because they are moving so fast. In fact, you might say the area where the spokes are located just looks like a fuzzy cloud. Keep that picture in your mind as we continue with the wave model here, because the wave model suggests not only are the electrons found in an electron cloud, but that both the energy and the position of electrons cannot be known at the same time. Similar to how the speed of a spoke and the position of a spoke cannot be known simultaneously. They're just moving way too fast. Well, we know now that electrons are moving at just about the speed of light around the nucleus of an atom. It is essentially impossible, according to what's called the Heisenberg uncertainty principle. It's essentially impossible for us to know both the energy and the position of an electron. That is the second primary main point of the wave model of today. Now, how does this look? Well, here is a model for you to copy down in your book of the wave model. We still have a densely packed nucleus with positively charged particles that we call protons. And there's also neutrally charged neutrons. We'll get to those in a moment. But around that positively charged nucleus, we have these negatively charged electrons zooming around very, very quickly at about the speed of light. And in this electron cloud, it's essentially impossible for us to know exactly where they are and how fast they're moving or how much energy they have at exactly the same time. Now, we can use mathematics to make predictions, and with those predictions, we come up with different possible shapes. And in high school chemistry, you will learn about the different spins and the different charges, or the different characteristics, I should say, of the electrons as they're spinning around the nucleus of an atom. It gets rather complicated, but we're not going to go that far with our class this year. So here we've got the wave model, which exists today, but we are constantly manipulating and adding to this model as we make new discoveries. So there are a few more terms I want to go over with you, which tie into these models and will prepare a foundation for us for future discussion about chemistry. So let's get right into it. We mentioned these subatomic particles in your vocabulary. Subatomic particles, as the name implies, are particles that are smaller than the atom itself. And there are three primary subatomic particles that we'll mention right now. The first are called protons. Protons are positively charged, and that is what is written in parentheses here, the positive charge. Don't pay attention to that. You know what? I should really change that to maybe a colon. I don't want you to be confused with sign. So protons have a positive charge. They are found in the nucleus. Now, you're going to have to remember all of these. And the way I remember protons and their charge is I think of pp, positive protons. Protons are positive. Think of pp. All right, the next one. The next one, and I'm just going to make these changes here as we go along. The next one are called neutrons. Neutrons have a neutral charge to them, and we symbolize or summarize neutral with this symbol here, which looks like a 0. Neutrons have a neutral charge, and they also are found in the nucleus. Now, the way I remember neutrons is I think of the first 1, 2, 3, 4, 5 letters, Neutr. Neutron, neutral. Neutrons have a neutral charge. Neutral subatomic particles are neutrons. So I've underlined certain things here. I'd encourage you to do that in your notes as well to help you remember which one is which as well. And now for the oddball one, the third one. The third subatomic particle, as I make these changes in our notes to help clarify things, the third particles are called, oopsie, didn't mean to do that, are called electrons. Electrons have a negative charge. Now, how can you memorize that? Well, electrons, negative, I don't know. You know, I use the process of elimination myself. I know that protons are positive, pp. I know that neutrons are neutral, neutral. And so by process of elimination, I know that electrons are negatively charged. I also know that electricity is the flow of electrons, and electricity with batteries always comes out the negatively charged terminal of a battery. But you remember it as you see fit. But protons positive, neutrons neutral, electrons negative. That is going to be very important information as we plow ahead next unit with chemistry. So underline it, memorize it, don't forget it. We'll come back to it. But for now, let's continue with a couple more words here. Starting with quarks. You see, we know more now than we did 100 years ago. And we know now that these protons, neutrons, and electrons, these subatomic particles, are also made out of smaller particles. And we call the whole group of particles that make up subatomic particles quarks. Why? Because it's a cool name, quark. And there are many different types of quarks. We're not going to get into them now, but we've got neutrinos and all sorts of subatomic particles, the most recent of which is called the Higgs boson. You may, if you're into science and the news, you may have heard about the Higgs boson being called the God particle. There are scientists who think the Higgs boson might be indivisible, like we used to think an atom was indivisible. We'll see if that comes to fruition or not. There's still so much we do not know yet about atomic structure. But how do we know about these things? Well, because we like to smash things. We have gigantic atom smashers or particle accelerators in different parts of the world. One of the largest is in CERN, Switzerland. It is the CERN particle accelerator, where they take subatomic particles, protons, neutrons, and electrons, and propel them at the speed of light using powerful magnets, and then smash them into barriers and study the bits and pieces left over to make their conclusions. It would be analogous to driving a car really, really fast through a swamp with lots of bugs, and then studying the bug splats on the windshield to see what kind of bugs lived in the swamp. That's exactly what scientists are doing now with these particle accelerators They're taking these known subatomic particles, splatting them into a barrier, and studying the bits and pieces left over. In a nutshell, that's basically what is happening as we learn more about all of these subatomic particles that, again, are divided into leptons from the quarks and gauge bosons, and there's the Higgs boson. All these funky different names I am not going to ask you to memorize, because by the time you're in college, there'll probably be a dozen more of these names as well. There are a couple of other words I want to go over with you that, again, are super important for this week and will lay the foundation for our entire next unit of study with chemistry. So let's begin here with atomic number. Atomic number is the same as the number of protons. Now, we'll learn a lot more about this next unit. But when we get to the periodic table, we will discover some of the information on a periodic table, including a number called the atomic number. And just knowing the atomic number, we will know how many protons there are in that particular element. The next term is atomic mass. The atomic mass is equal to the number of protons plus the number of neutrons. Now, you don't have to worry about figuring this out right now or truly understanding the importance of this at this point. Just memorize the difference between atomic number and atomic mass. Next marking period or next unit, we're going to unpack this in a lot more detail. So stay tuned. And one final term I want to introduce you to here, and that is the word isotope. An isotope is an atom with a different number of neutrons. For example, all of you are familiar at least with the name of hydrogen. Normally, hydrogen has one proton in it, but there are other isotopes of hydrogen called deuterium and tritium. Deuterium and tritium are both radioactive because they have a different number of neutrons. They have extra neutrons. That's why they're called isotopes. Now, a little side note here, when making a nuclear bomb, and we'll get into that later on in the year, not how to make one, but the energy involved and the science behind it. But there was a project, a famous project during World War II called the Manhattan Project. And it involved isolating what was called hard water. Hard water was radioactive water comprised of water made up of hydrogen and oxygen, but the hydrogen in the water were radioactive isotopes of hydrogen. Hard water, I misspoke. It's not hard water, it's heavy water. We all have hard water if you have well water. Hard water is mineral water. I meant to say heavy water. And it's called heavy water because it is heavier. It has a greater atomic mass because there's a greater number of neutrons. So those countries around the world that might be trying to gain the ability to build nuclear bombs need to obtain heavy water, which have certain isotopes, heavier isotopes of hydrogen. All right, that's a lot of information for today. You don't have to understand these last three terms all that much. Again, I'm just trying to lay a foundation for you for our next unit of study in chemistry, but I am asking you to at least memorize what these terms mean for Friday's quiz. So tomorrow we'll do an activity. So you have a couple of days to study this information. But until tomorrow, I'll simply say bye-bye.